Hi, welcome to Chem with Chem. This is a full workthrough of the CSEC Chemistry Paper 2 from the January 2020 edition. Please like, share, and subscribe. Please check out the links below this video in the descriptions for direct access to other videos like this one. Use the timestamps available to toggle to your favorite questions. Enjoy. Question 1. The rate of reaction of magnesium with a solution of dilute sulfuric acid can be investigated by measuring how long it takes for a specific volume of gas to be produced. All right, I feel like I'm reading an answer, I'm reading some information right there, crucial. Andrew conducted 2 experiments to investigate factors that can affect the rate of reaction between magnesium and sulfuric acid. In experiment 1, magnesium strips were added to 50 cm³ of 2 moles per dm³ sulfuric acid in a 250 cm³ conical flask. Oh, that's a mouthful. The volume of gas produced over a period of 6 minutes was measured, and some of the measurements are shown in Figure 1. The data recorded for experiment 1 are summarized in Table 1 on page 6. So before we get to Table 1 on page 6, because we don't want to be scrolling up and down, we want to keep the page fixed. We're just going to record the readings and we're going to write them in our table. All right, so let us look at the gas syringe. So these are the readings that we're going to be recording. All right, and a few of them are done for us already, so we just need to record the readings for these. Now, whenever we're reading, whenever we're going to take readings, it's very important that we determine the scale or the gradation on the instrument. So for this gas syringe, each of these little stroke that we're seeing, each of these little marks, each of them represents 1 centimeter cube. And we're looking at what volume is produced at the different times: 0.5 minutes, 1 minute, 2 minutes, 3 minutes, at minute number 4. All right, so we're just going to write these down, and then we're going to fill them into our table in a bit, and then we're going to use them to more than likely plot. That is what question 1 is about: some form of data analysis, mirroring what would normally be done in the lab. So the lab and the theory, everything goes hand in hand. All right, so let's just get right into our reading. So at minute 0.5, that's half of a minute, we have the volume produced here would be 1, 2, 3, that looks like 6, that would be 6 cm³. At minute 2, well, we're not at minute 2 as yet. At minute 1, the volume here is 11 cm³. And at minute 2, this is, let's see, 11, 12, 13, 14, 15, 16. This is 16.5 cm³. At minute 3, this is 19 cm³. At minute 4, the last one, we have, this is, right, 20, sitting exactly in the middle of 20. So this is 20 cm³. So we're going to take these readings and we're going to fill them out. We're going to fill them out in our table. So just before we fill in those values, as we said, we don't want the page we don't want to be scrolling up and down too much. We're just going to take care of part A before we go into filling in those values that we just wrote down. Define the term rate of reaction. And this answer was given in a subtle way in the question. Let's just look back at that. This answer was given. The rate of reaction of magnesium with a solution of dilute sulfuric acid can be investigated by measuring how long it takes for a specific volume of gas to be produced. Whenever we're talking about how long, we're talking about time. how long it takes a certain amount of a substance to be produced. It could also be how long it takes a certain amount of substance to be used up. So therein lies our answer. So let's go back down to part 1 of A and answer that first question and just feel good about getting 1 mark, an easy 1 mark. So the rate of reaction is the change in concentration of reactant or product per unit time. In other words, how long it takes a certain amount of a product to be formed, or how long it takes a certain amount of a reactant to be used up. Right, and then we'll move on to part B. Part 1 of B, and we're just going to write in the values that we just read off. So they did at 0 minute, 5 minutes, and 6 minutes for us. So we're just going to fill in our values for half a minute, minute 2, minute 3, minute 4. So at half a minute, we had the volume being 6. At a minute, we had it being 11. At 2 minutes, we had it being 16 and a half. At 3 minutes, 19. And at 4 minutes, 20. Right, so we're going to use these values, so write them down. We're going to use them in the next section. Part 2 of B. Use the data in table 1 to plot a graph of the volume of gas produced against time using the axes below. So we have the data, we just read them off. We're going to just plot. But before we plot, we always need to know the scales on each axis. If not, we're not going to be accurate. Accuracy is very important here. So on the x-axis, we see that for every 2 centimeters that we have, it's been used to represent 1 unit, right? So it means that each of those millimeter, those little ones, would be representing 0.1 minute. And so it means that here we would have 0.5, here we would have 1.5, and so on. So we'd have 0.1, 0.2, 0.3, 0.4, then 0.5, and so on. On the y-axis now, we see where 2 centimeters are being used to represent 5 centimeter cube. So it means that each of these little millimeter box, each of them would be representing 0.5 units or 0.5 cm cube. All right, so we go right into plotting, and please note that they have already plotted 3 for us at 0, at minute 5, and at minute 6, and they've used encircled dots. So we're just going to continue along that line. Okay, so at 0.5 minutes, at half a minute, so let's find half a minute on the x-axis. It's here, so we're going to go up at half a minute. We have the volume being produced. The volume being produced is 6. So right here, the first millimeter after 5 is 0.5. So that's 5.5. Another 0.5 to that will make it 5.6. So that will take us here, and we're going to use let's change to, okay, we can keep this blue. All right, then at minute 1, at 1 minute, 11 cm cube. So this is 10.5, and this would be 11. So at 1 minute, 11 cm cube. So we plot at 2 minutes, 16 and a half. Minute 2, so we find 2 on the x-axis, and we go all the way up. This is 15, 15.5, 16, 16.5, and I'm just marking it here so we can trace it. You would trace it with a pencil and you rub it off in the exam. All right, and then at minute number 3, we have 19, so we find 3, and we go up to 19. We can just look for the 20 line and we come down 2 spaces. That's one way to go about it. So this is 20, so this would be 19.5, and then this would be 19. So 19 is here. Minute 4 is 20. Minute 4 is 20 cm cubes. So here we are. So we now need to plot, and we want to do that free-handedly. We want to just get one smooth curve going that levels off from 20, levels off or it starts to level off at 20. So we'll come up. Let's see if we can do this in one go. All right, so we'll work with this one. We want the curve to be a little smoother on the last part, but based on the device I'm using, I'm not getting it like that. We don't want it to be flat right here. We want it to be smooth. So in the interest of time, we'll take this one. Okay, so for the other questions, we're going to let this part remain, and I'll just read the other questions and we'll just answer as we go along. So most of the a good number of the other questions come from using the graph. So from your graph, so part 3, the first one, using the graph. From your graph, determine the time taken for the reaction to be completed. So if we check the graph, we realize that at minute 3, we had 19 cm cube being produced, and at minute 4, we had 20. And then after minute 4, we still had the same volume. No increase in volume was there. So we had 20 at minute 4, at minute 5, the same 20, at minute 6, the same 20. So it means that this reaction would have come to an end, or this reaction ended from minute number 4. So let's put that down. So it would be minute 4, or we could say 4 minutes. The time taken, 4 minutes. And that would give us the mark. Now, they're also asking in the next question, they're asking part 4. During which time interval was the rate of the reaction fastest? During which time interval was the rate of reaction fastest? And we can look back at for this, we can look back at the table that we filled out just now. So just gonna do a little. So we had the time, and we had in minutes, and we had the volume in cm cube. So if we can get this one without even looking at, without using the graph. We can just look at the table. We can just look to see which time interval gave us the largest volume. We want to say largest amount produced in the shortest amount of time, and that is what that's how we would know that we had the fastest rate, or during which time interval was the rate of the reaction the fastest. So it would be, looking at the table here, it would be from 0, the time interval would be from 0 to half of a minute, 0 to 0.5. That's the time interval that would have given the fastest rate. Let's just highlight that. So the fastest rate would have been from 0 to 0.5. And this is right here, 0 to 0.5. Let's highlight that on the graph itself. We have the graph being steepest right there. Okay, and if we don't want to answer the other question prematurely. So it's from 0 to 0.5 minutes between. So that's the time interval, 0 to 0.5 minutes. And in part 5 now, they want to know, they want us to tell or to give the reason to explain the answer. And so we could state that that part of the curve is steepest, but we can do better than that. We can actually give empirical evidence, all right? Because we can do the actual rate. We said earlier that the rate of a reaction is the changing amount of substance formed or used up per unit time. Per unit time means we're going to be dividing by time, how long it takes. So if we look moving from 0 to 5 seconds, we had no gas at 0, but we had 6 cm cube form, 6 centimeters cube form after half of a minute. So the rate right there would be, so for 0 to 0.5 minutes, the rate would be 6 cm cube over 0.5 minutes, and that would give us a rate of 12 cm cube. That would give us a rate of 12 cm cube per minute, and that was the highest rate for the entire reaction. In moving from half of a minute to 1 minute, the change would have been, let's see, 11 minus 6, that's 5, a change of 5. So that would be 5 over half of a minute, which would be a rate of 10 cm cube per minute. And then if you look at 1 minute to 2 minutes, the change in volume is 5.5 divided by 1 minute, so that would be 5.5 cm cube per minute. And it kept on getting slower, or the rate kept getting lower as time progressed. So the fastest part of a reaction is normally the first part. So we call that the initial rate. So in this case, it would be from 0 to 0.5. And given the reason, we would state that the highest rate of the reaction was obtained there, and we would of course give this part that we have right here. We would give that as our evidence to support that, and we would get our full marks. All right. So part 6 now, they want us to, from your graph, determine the volume of gas produced at 2.5 minutes. 2.5 minutes. So we need to look for 2.5 on the graph. On the x-axis, we're looking for 2.5. 2.5 is here. So we need to draw a straight line using our ruler. Find the volume produced. Wherever that cuts the graph, we would use our ruler again to draw a straight line going across. And wherever that line cuts the y-axis, we read off our values. So we said that we're going up, each millimeter on the y-axis is used to represent 0.5 cm cube. So let's check what we have here. This would be 15.5, 16, 16.5, 17, 17.5, 18. That looks like 18. That looks like 18.5 cm cube. So for part 6, we're going to use the 18.5 cm cube, and let's just highlight that in green. Then we're going to move down to that section. So in part 7, we're going to use the volume that we just found and answer the question. So use your answer in B6 to determine the number of moles of gas produced at 2.5 minutes. So at 2.5 minutes, we just saw that we got 18.5 centimeters cubed. And we're always given something to use. We never left on our own. So 1 mole of gas occupies 22.4 dm cube at standard temperature and pressure. All right, but our value here is in centimeters cubed. So to get a mark, we're going to have to do some form of conversion. So 1 dm cube is the same as 1000 cm cube. So for the first mark, we're going to convert our 18.5 centimeters cube. We're going to convert that to dm cube. So we'll say 18.5 cm cube divided by 1000 cm cube, and that will give us our volume, the volume that we just found, that will give us our volume in dm cube. So we want to keep apples with apples, right? So that's 18.5 divided by 1000. We're going to take that 3 decimal places to the left, which will give us 0.0185 dm cube. Then we're going to start out with a statement of fact. So our statement, so let's keep this by itself. So we'll get a mark for this. Then we'll have our statement of fact, which states from what we're given, 1 mole of the gas we're concerned with, any gas as a matter of fact, occupies 22.4 dm cube. Now we want to find out how many moles, so we put X. How many moles of gas would we have been occupied by 0.0185 cubic decimeters? So we'll cross multiply, and when we cross multiply, we take things across, well, the diagonals. That's a little redundant, but yes, going across. So that X there is not saying it's wrong, we're just going across. So it means then that 22.4 dm cube times X is equal to 1 mole times 0.0185 dm cube. And if we want to make X the subject, we have to get rid of everything that's around X. So we'll need to divide by 22.4 dm cube on both sides. All right, let's use red to cancel out. So 22.4 dm cube, 22.4 dm cube, and whatever we're left with, that will be our answer. So that will be 0.0185 divided by 22.4 dm cube. And of course, we would expect to get less than a mole. So our answer here is 0.000826. 0.0000826 moles, or we could write that in standard form, 8.26 times 10 to the minus 4 moles. And that would have given us our full marks. So 2 from here and 2 from the conversion that we did earlier. So that would take care of this section. Part 8. Andrew wanted to identify the gas produced. He placed a lighted splint in a sample of the gas, which extinguished with a squeaky pop. Deduce the identity of the gas. So once we hear about a flame, a lighted splint being extinguished with a squeaky pop, then the gas in question is hydrogen. Hydrogen is actually flammable, so that squeaky pop is a mini explosion that we're actually hearing, right? And of course, if it were a larger volume, then we'll probably hear an explosion that is not so squeaky, right? So that would be hydrogen. And of course, be sure to check out qualitative analysis video made simple. Check out the card above for it. There we look at how to identify cations, anions, and also gases, including hydrogen. Part C, and we're almost close to the finish line. We can see the finish line, at least the finish line for number 1. We're almost seeing the 25 marks. We just have 4 left, so we would have already amassed 21. Good, but we want to get better. All right, part 1 of C. Andrew's second experiment required the use of the same mass of magnesium but in the powdered form, instead of strips. State the factor that Andrew is now investigating. So strip the first time, magnesium strips the first time, but magnesium powder the second time around, but the same mass. Andrew is now looking at the factor of particle size, or what we call surface area. And we would have worked a question similar to this. You can check that out as well. The card is provided above. Similar question. It was just modified somewhat. And part 2, write a balanced chemical equation with state symbols for the reaction that occurred between magnesium and sulfuric acid in the experiment. Magnesium, Mg, it's a solid, plus sulfuric acid, H2SO4, which is aqueous. Acid is in the presence of water, would have dissociated. And of course, it's a metal, reactive metal, and an acid. So we're going to get a salt and a salt, not a salt. We're going to get a salt and hydrogen gas. So the salt here would be magnesium sulfate, which is soluble. So we'd have aqueous. This is AQ, we've written in the little bracket there. What's that, subscript, and then we would have hydrogen. And whenever we write elemental hydrogen, we have to write it as H2. Again, anything that ends in, any element that ends in or gen is diatomic. And let's see, this is it. This is just balance right off the bat for 2 more marks. So for the last mark, to just top this up for 25 out of 25. State one factor other than the factor investigated by Andrew, which can affect the rate of a reaction. And please notice they did not give us any clue here. So we can't use surface area from C1 above. We'd have to state any of the other factors that could actually affect the rate of the reaction in this case. And we're looking at the reaction that Andrew is actually looking at, magnesium and sulfuric acid. So surface area or particle size is out. So the next thing would be temperature. Temperature is another factor that could actually affect the rate of this reaction. Or we could also give concentration. Altering the concentration of the acid would actually could affect the rate of the reaction. All right, and just like that, we would have gotten full marks, 25 marks. All right. When oxidation and reduction occur together during a chemical reaction, the reaction is described as redox. Redox, meaning oxidation and reduction are taking place at the same time, not redox, the brand. Some substances can act as oxidizing agents while others act as reducing agents. The equation for the redox reaction between aqueous copper-2 chloride and aqueous iodide is given below. 2Cu2 plus aqueous plus 4I minus, that's iodide aqueous ions, to give 2 copper iodide solid and iodine in aqueous medium. Define reduction in terms of oxidation states. Now, oxidation and reduction can be defined in 4 ways, but we want to define reduction in terms of oxidation states. So we'll just get right into it. Reduction is the decrease in the oxidation state of a substance. Part 2, deduce the oxidation state of copper in copper iodide. All right, so let's single out copper iodide. It's an ionic substance, so we'll have to look at some of the rules for assigning oxidation number. Now, in an ionic compound, the sum of all the oxidation numbers of the elements present is equal to 0. So iodide here, like all the halides, when they're in compounds, ionic compounds, their oxidation number is, when the halides find themselves in binary compounds, binary metal halides, then their oxidation number is -1. So it means then, whatever the oxidation number of copper is, when we add it to the -1, When we take the sum of everything, we should get 0. So we're saying X, whatever the oxidation number of copper is, plus -1 is equal to 0. So what must we add to -1 so we can get 0? So our answer would be +1. So we write +1. So the oxidation state is +1. Please note that for oxidation state, we write the sign before the number. And for charges, we write the number before the sign. Even though you'll see in many textbooks, you'll see it being used interchangeably, this is the correct sign convention. All right. Define part 3, define the term oxidizing agent. And in our definition, we don't want to say about the word oxidizing, all right, or oxidize. So we'll just say exactly what it is. It's a substance that accepts electrons from another substance and is itself reduced in the process. So it's called an oxidizing agent because when it accepts or gains electrons from another substance, that other substance in the process becomes oxidized. It's a transfer of electron process. So those electrons are not coming out of thin air. They have to come from something. So it's like in accounts, to every debit, there's a corresponding credit. Money is going somewhere and money is leaving somewhere. So the oxidizing agent is what will accept those electrons. And when the oxidizing agent accepts the electrons, the oxidizing agent itself becomes reduced, because reduction can also be defined as a gaining of electrons. All right, and oxidation can be defined as a loss of electrons. Oil, oxidation is loss, reduction is gain. So let's just get that definition for oxidizing agent in. Part 4, with reference to the equation above, state with a reason which substance is acting as an oxidizing agent. Now, to really get this well, it's best if we assign. We're recommended to assign oxidation numbers to all the species that are present on the left-hand side. So this is our left-hand side of the equation, writing in blue, and this is our right-hand side, RHS. So we're going to be looking to see which of them, in moving from left to right, would have undergone a decrease in its oxidation number. And then from our definition above in part 1, we said that reduction is a decrease in the oxidation state, and the oxidizing agent is itself reduced. So we're looking to see which species would have undergone a reduction in its oxidation state, or would have experienced a reduction in its oxidation state. So we have Cu2 plus, so the oxidation state would be +2. We have 4I minus. The oxidation state for the iodide there is -1. Now let's look at what is happening over the right-hand side. The copper in copper iodide, as we stated earlier, the oxidation state is +1, and the iodide itself in copper iodide is -1. The iodine there is elemental iodine, though it's in the presence of aqueous medium, presence of water, it's 0. So in moving from the left to the right, we realize that only one species would have undergone or would have seen a reduction or a decrease in the oxidation state, and that is the copper 2 plus ions. Its oxidation state decreased from +2 to +1. So that means the Cu2 plus is our oxidizing agent. So we're going to state this given the reasons. So we'll say so Cu2 plus is oxidation state decreased from +2 to +1. So it was reduced. So Cu2 plus is the oxidizing agent, and would have gotten full marks for stating that. Part 5. Solution A was added to a small portion of an aqueous solution of potassium iodide in a test tube. The colorless potassium iodide turned brown. State whether solution A contained an oxidizing agent or a reducing agent. All right, so let's try to visualize that. We're given a test tube which contains aqueous potassium iodide, which is colorless. And then solution A is added to this solution of potassium iodide, and the potassium iodide change from colorless to brown. And we should state if solution A is an oxidizing or a reducing agent. Any change that occurred in the potassium iodide solution would have been brought about because solution A was added. All right, so to begin with, potassium iodide is a reducing agent. So in the presence of an oxidizing agent, then we're going to get a characteristic color change in our potassium iodide from colorless to brown, as was stated in the question. So it means, therefore, that solution A then would contain an oxidizing agent. Explain your answer in A part 5 above. So we're going to just summarize what we just said a while ago. We probably were answering part 6 while we went about the explanation just now. So we're going to state that aqueous potassium iodide is a known reducing agent, and we're going to give its oxidation state and state what happens to it when an oxidizing agent is added. Aqueous potassium iodide is colorless and it's a known reducing agent. And in aqueous potassium iodide, the oxidation state of the iodide is -1. So when the iodide in potassium iodide is oxidized, which is brought about by whatever oxidizing agent is in solution A, then the iodide is oxidized from -1 to 0, giving elemental iodine, which gives the solution the brown appearance. And they want us to write a balanced chemical equation to show the formation of the brown product. The brown product is iodine in the presence of aqueous medium. And persons might be wondering, but sir, iodine is a dark purple solid. But the iodine that is being formed here is being formed in aqueous medium, so it would be brown. All right, so we're going to write what happens. We would have iodide I minus aqueous to say it's in the presence of water, and we're going to, so this is the species that we have, and then this species now is going to be losing electrons. Electrons is going to be taken away from it. Oxidation is loss of electrons. So electrons have a negative charge. So if an electron is being removed from I minus, it means that we're going to end up with I in the elemental state without a charge. And of course, this would still be in aqueous medium, and we're going to have the electron that was lost. We're going to have that being available now, because as we said earlier, it's a transfer of electron process. But of course, this process happens a second time because we could not have I, elemental I by itself. Anything that ends in "-ine" or "-gen" is diatomic. So when this process happens a second time, we would have the formation of I2, but we would need 2 iodide ions, and we would get 2 electrons or 2 moles of electrons being liberated and available for transfer. Some books will show you 2I minus 2 electrons, but the best convention or the correct convention is to do it like this, where we show for loss of electrons, we show the electrons on the right being liberated on the right side of the arrow. So we'll have the species, and we'll have what happens after the electrons are lost, and we have the final species plus the electrons that are liberated and are now ready to be gained. All right, so that would give us 2 more marks. Part B. When a piece of zinc metal was added to an aqueous solution of copper-2 sulfate in a test tube, a chemical reaction occurred as shown in the equation below. Zinc solid plus copper-2 sulfate solution to give zinc sulfate and copper solid. Now, I hope you've noticed the nature of the question so far. If you've done labs related to these questions, then all the better. If you haven't done so, you can check out the link below or the card above for a lab that is similar to this, where we looked at the reducing ability of metals, except that we did not give the names of the metals. We had them as A, B, C, D, etc. So this is displacement, but in displacement, redox is taking place. It's actually a redox process. So we're asked to describe what is observed with regard to the chemical reaction that occurs in the test tube. So first things first, let's look at how things are at the beginning, and then let's look at whatever changes are taking place. So the zinc, as we know it, zinc is a gray solid. The copper 2 sulfate is a blue solution. Zinc sulfate is supposed to be colorless. We'll address that in a bit. And the copper solid would be a pinkish brown or a pinkish brown solid. All right, so let us look at what will happen. As the reaction progresses, we would expect to see our gray solid dissipating, which is the zinc. So the gray solid, the strip of zinc metal, the gray solid, which is the strip of zinc metal, would dissipate, DISSI. Also, as the reaction progresses, the blue solution would actually decolorize as Cu2 plus ions are being reduced to give us elemental copper. So the Cu2 plus ions in aqueous medium is what's responsible for the blue appearance of the solution. So as the copper ions become reduced, then we'll have the blue solution decolorizing. So it's the blue solution decolorizes. And of course, for the formation of the solid, the copper, we would expect to see pinkish brown deposits, pinkish brown solid deposited or deposits at the bottom of the test tube. And that would have given us full marks. That would give us full marks. Part C. One of the substances in the equation in B on page 11 is acting as a reducing agent. Describe a simple laboratory test that could be used to identify a reducing agent. Now, if we have a reducing agent, well, for a reaction to be called a redox reaction, oxidation and reduction must be taking place simultaneously. So if we have a reducing agent, or we suspect that a species is a reducing agent, then we need to test it with a known oxidizing agent that gives a characteristic color change. So we could use acidified potassium manganate 7, same thing we call potassium permanganate. We could use acidified potassium dichromate 6, right? And that is orange. Dichromate, acidified potassium dichromate 6 is orange. Acidified potassium manganate 7 is purple. So let's just look at one of them, and you can just make a note of the other one. So what we would do, we would test the suspected reducing agent with a small amount of acidified potassium manganate 7 solution. If the substance is a reducing agent, then it would change the acidified potassium manganate 7 from purple to brown or to colorless. It doesn't always go from purple to colorless. Sometimes it stops in between at the +4 oxidation state, where we get Mn, Mn with the +4 to brown or to colorless. So let's just get this down. And just like that, we would have gotten 2 more marks, and a total of 15 marks. Now, this question is an organic chemistry question. It's at the early stages, looking at homologous series. So let's just get right into it. List 3 characteristics of a homologous series. All right, so the word homologous, looking at the word homologous, we're seeing same and we're seeing logos. Homo means same, logos coming from a group. So homologous series, members of a homologous series would have the same general formula. And I believe we will delve into that a little bit more later on. Same general formula. They'll also have the same functional group. And the functional group is the part of the molecule that gives it its characteristic chemical properties. That's a part of the molecule where a chemical reaction actually takes place. Members of the same homologous series would have the same ending name. So this is like traditionally, where members of a certain family will have the same last name. So members of the Browns family will have the last name Brown. So if we're looking at the alkanes, all the members of the alkane series or the homologous series called the alkanes, their last name would end in "ane." So they have the same name ending or the same last name, for want of a better word. And also we could look at the physical properties showing a steady variation based on increasing number of carbon atoms, but we're only going to give 3. Part B, 1. Draw the fully displayed structural formula for compound A, which has the molecular formula C3H8. C3H8. Structural formula C3H8. So this looks like it is from the alkane series without us preempting the other questions. So we're just going to draw our 3 carbons. This chain is made up of 3 carbons, and of course, we normally add on our hydrogens. Each carbon must be taking part in 4 bonds because carbon is tetravalent. So there we go. And this is what we call our fully displayed structural formula, showing how the atoms are arranged to each other in space, or how they're bonded to each other in space. Part 2 of B, state the homologous series to which compound A belongs. So compound A, just now we saw that the molecular formula was C3H8. So this would belong to the alkane series, alkanes, and they want us to, for part 3, to write the molecular formula for the compound which has 5 carbon atoms of the homologous series stated in B2 above. So the one with 5 carbon atoms, we will use the general formula CnH2n plus 2, and that will give us the molecular formula. So if I want 5 carbons, we're going to put 5 where N is. So that would give us C5, then 2 times for H. 2 times 5 is 10, plus 2, 12. So that would be C5H12. And I want us to draw the fully displayed structural formula for compound. Oh, this is a different question. Part C. Part 1 of C, draw the fully displayed structural formula for compound B, which has the molecular formula C3H6. C3H6. So this is a different compound. This is from our alkene, and there's a carbon-carbon double bond. So it means that our compound here is unsaturated. So each carbon again must be taking part in 4 bonds. All right, so let's just adorn our carbons with the hydrogens, C3H6. And just like that, we would have amassed some more marks. Part 2, state the homologous series to which compound B belongs. And compound B that we just drew had the molecular formula C3H6. So we know that this is from the alkene series. General formula for members of the alkene series is CnH2n. And part 3, write the molecular formula for the compound which has 5 carbon atoms of the homologous series stated in C2 above. 5 carbon atoms from the alkene series, we're going to put 5 where we have N, so that would give us C5, and then H, 2 times 5 is 10, so that would be C5H10. Right, and then now for part D, the last part of this question. For each of the following homologous series, write 1, the general formula. And they want the general formula for carboxylic acid. Now this, I won't say this one is tricky, but what's very important to note is that we will write the general formula, but the last part, the functional group of the carbon in the functional group of the general formula is normally counted if we're actually writing out the molecular formula. So for our carboxylic acid, it is Cn, N represents the number of carbon atoms, H2N plus 1, COOH. And then they want the general formula for alcohols. It's, and I'm gonna just put it in right here, CnH2n plus 1 OH. So I'm just gonna highlight the functional group for emphasis. So the functional group for alcohols is, let's change our color. The functional group for alcohols is OH. And the functional group for carboxylic acids is COOH. So those are the parts that give the molecule, that gives the molecules their chemical properties. And we move on to part 2. We're stating the name of the first member of the carboxylic acid series, just the name, and we're also stating the name of the first member of the alcohol series. So the first one for our carboxylic acid, it would be methanoic acid. Methanoic acid. All right, and remember that the prefix meth means 1, eth means 2, prop means 3, but means 4. So let's just jot that down in the corner here. Meth means 1C, eth means 2C, prop, 3 C's, but, 4 C's, pent, 5 C's, and so on. And so for the, so it's the prefix plus the last part of the name. So in this case, it's meth plus anoic acid. Now, when you're looking at the alcohols, and we're just answering, we're not going into a lesson. The first one would be methanol. The second would be ethanol. The third would be propanol. The fourth would be butanol, and so on. So just like that, you would have amassed another 15 marks. So one step closer to us getting our. This question is an electrolysis question. Let's just get right into it. Part A of number 4. Jack was required to conduct an investigation on the electrolysis of concentrated sodium chloride solution. Very important word there, concentrated sodium chloride solution. It makes a big difference. Identify 2 ions present in the electrolyte and include their state symbols. If we're talking about concentrated sodium chloride solution, then naturally we're going to have sodium ions, Na plus ions, aqueous, it's in aqueous medium. Would also have chloride ions, that's Cl minus. And they ask for 2. We could also give, we'll just put this on the side, we could also give H plus ions, aqueous, and we'd have OH minus ions as well. But they ask for 2. Next question. State 2 factors that affect the discharge of an ion in the electrolyte during electrolysis. So we have 3 factors. We have the position of ions in the electrochemical series. We have relative concentration, and this is for halides. electrolytes containing halide ions. And we're only going to give two. We can state the other one, the nature of the electrode used. Part 3, predict which ions present in electrolyte will be attracted towards the anode. So what I normally do here, or recommend that we do, we just remind ourselves what the anode is. The anode is the positive electrode. So opposite attracts, so we'll expect the negative ions, aka the anions, to be attracted to the anode. So the anions that would actually, the anions here are OH minus ions, aqueous, and Cl minus ions, aqueous. So those are the ions that would actually be attracted towards the anode. They will migrate. And of course, the one that gets discharged or liberated now depends on the factors that were just mentioned in part 2. So normally, OH minus would be liberated because it's at the bottom of the electrochemical series and it requires less energy to be liberated, right? But in this case, we have concentrated sodium chloride solution, and we said that the concentration makes a difference. So this time around, the relative concentration would actually trump the position of the ion in the series. So chloride, though chloride is higher in the electrochemical series of anions than OH minus, would find that the chloride ions would actually get the go ahead. So just a reminder, the electrochemical series for anions: carbonate, sulfate, nitrate, chloride, bromide, iodide, and OH minus. So under normal circumstances, if we were looking at a dilute sodium chloride solution, then the OH minus would be liberated preferentially. But in this case, we have a concentrated solution of sodium chloride. So concentration trumps relative position in the electrochemical series. So as we said earlier, the chloride would actually get the nod. And if the chloride gets the nod, we're at the anode. So oxidation occurs at the anode. So we would have loss of electrons taking place. So we would have our chloride ions, Cl minus, aqueous, and we put our arrow, and that would give us chlorine, elemental chlorine, plus the electron that's given up. But of course, chlorine is diatomic, so we'd have to write this as Cl2. So this reaction would take place twice, and the moment it happens, we'd end up with chlorine being formed, Cl2. So this is our balanced chemical equation for what's happening at the anode. 2Cl minus aqueous to give chlorine gas, that's Cl2, plus 2 moles of electrons. And that would have given us all of 2, 4, 6, 8 marks. This question is for 15 marks, so we're a little over halfway there. Part 5, write a balanced chemical equation for the reaction at the cathode. So we would have two types of ions migrating to the cathode. We would have Na plus ions, aqueous, and we would have H plus ions, aqueous, actually migrating to the cathode. But only one of them would actually be liberated. So in this case, our hydrogen would be liberated preferentially over our sodium. So even though there is a higher concentration of the sodium, the Na plus ions, over the H plus ions, we would not have the concentration of we would not have concentration playing a role here in which cation is liberated. So even though more Na plus ions would be there relative to H plus ions, the H plus ions would still be liberated. It would require too much energy for the Na plus ions to actually be liberated. So this is the opposite of bonding. Breaking up in this case is really hard to do. So the H plus ions would actually get the nod, Just a reminder, our electrochemical series. So hydrogen would actually get the nod. So we're just going to look at what happens in this case. So reduction is occurring at the cathode. So we'd have the H plus ions being discharged. So we'd have gain of electrons this time. And please note that we have the species plus the electrons, and then we have whatever the final product is. But of course, we know that we cannot write hydrogen as just H. Anything that ends in or gen is diatomic. So the moment this reaction occurs, and it occurs a second time, we'd have the atoms of hydrogen combining to give us H2. So we just need to put a 2 in front of the H plus and in front of the electrons, and we're balanced. So that's that. Part B, state whether each of the substances given in table 2 are classified as conductors or non-conductors. Magnesium ribbon, metals are good conductors of electricity. We're assuming that they're talking about electricity, seeing that we're on an electrolysis question. So magnesium ribbon would be a conductor. Plastic ruler is a non-conductor. An aqueous solution of magnesium chloride. Aqueous solution of magnesium chloride. Magnesium chloride is an ionic compound. So in aqueous medium, the ions would be set free and can carry a current should a voltage be applied. So this would be a conductor. Conductors allow electricity to pass through them. I saw something the other day, properties of a conductor. It does not give back phase change. Not the kind of conductors we're talking about here. We're talking about things that allow the passage of electricity through them. Part C, carbon is an example of a non-metal. State 2 uses of carbon. Now, the uses here are many. We're going to look at the direct uses of carbon. Carbon can exist in 2 forms. We call those allotropes. We can have carbon in the form of diamond. We can have carbon in the form of graphite. So for as diamond, carbon is used as jewelry. Right. It's also used as drill bits. We just need one. The only thing that can be used to cut diamond is another diamond. And as graphite, carbon is used to make electrodes in industries. It's also used to make the quote-unquote lead in pencil points. And just like that, we would have gotten the remaining 7 marks. So this is out of 15. This question is on organic chemistry, reactions of esters, reactions of organic compounds, to be more specific. And we're just going to kick it off. Compound C, part A. Compound C is a sweet-smelling compound which is often used in flavoring and perfumes. All right, so once we hear anything relating to sweet-smelling compound in organic chemistry, then we should be thinking about ester and ester. Once we hear sweet-smelling compound, we should be thinking about an ester. All right, so they want us to actually name compound C and to give the homologous series to which it belongs. So we know it belongs to an ester. Sweet-smelling compounds, esters tend to be fragrant, at least the shorter chain ones. All right, so in naming an ester, this is how we do it. We identify, we verify that it's an ester by looking for the ester linkage, and we see the ester linkage here. So it's C double bond O O. Now normally put a little squiggle line to show those are sticky ends, which are actually bonds that are attached to other parts of the molecule. So that's the ester bond. So we start off knowing it's an ester by saying bond, ester, bond. So we have an ester linkage. All right, so two things make up an ester. An ester is formed from an alcohol and an organic acid. So the alcohol part is at the end. The alcohol portion is at the end. So this part is coming from our alcohol, and the part at the front is coming from our acid. Now, when we're naming the ester, we name the alcohol part first. So even though the alcohol part is at the end, we name the alcohol part first, and we name the acid part last. So let's check out what we have here. For the alcohol, we have a CH3 group. So this alcohol, this part of the ester was formed from an alcohol that is 1 carbon long. So that is definitely coming from methanol. So this is coming from methanol. So we will name this part methyl. So we're not saying this is methanol, we're saying it's coming from methanol. So this is really the methyl group. And since we name the alcohol part first, we will say that this is methyl, that's the CH3 group. And then the other part coming from the acid now, this part, the first part or the front part, it's made up of 3 carbons, 1, 2, 3. So that would have been formed from propanoic acid. So the name of the compound would be methyl propanoate. Methyl from the alcohol part, propanoate coming from the acid part, which is propanoic acid. So this compound is methyl propanoate. Methyl propanoate. And the homologous series, as we said earlier, is an ester, or is ester. All right, and that would have given us 2 marks. Let's complete this for the O. Draw the fully displayed structural formulae of the 2 molecules that are produced when compound C is hydrolyzed. All right, so let us clear our screen so we can get a good understanding of what's happening here. We want things to be as clear as possible. So hydrolysis, whenever we see hydrolysis, we know it has to do with the splitting of water. So to be able to do the backward reaction or to break up this compound, we have to understand what happened when it was formed. When the compound was formed to begin with, we would have had the OH. We would have had the OH from our acid joining with the H from our alcohol. And that part would have been pinched off, for want of a better word, to give us our water. So in the backward reaction or the reverse reaction, which is what we're doing now, we're going to be, let's clear up the molecule. We're going to look in the ester bond, and so we're going to do a little background check, and it's just for us to appreciate how we got the compound in the first place. Because if we know how we got the compound in the first place, then it's easier to actually break it apart. All right, so we're going to draw propanoic acid. We're going to draw propanoic acid. So propanoic acid is CH3CH2 COOH. Let's put on the hydrogens. So that's propanoic acid. And we're going to draw methanol beside it, and we're going to draw methanol in blue. So we're going to put the OH part of methanol at the front, and we'll have the other part of the molecule, CH3OH. So this is our propanoic acid and our methanol. So propanoic acid is in red. So let's just, so this is propanoic acid, and this is our methanol. So these are the formula of the two compounds. So we can just do that right away. So we'll do that, and that's the answer. But I just want us to look at how we get the joining, how we get them forming the ester bond. So under the right conditions of heat, acid catalyst, and under reflux, we would have, let's use a different color, we would have the OH from the COOH functional group of the acid. We'll have that part actually going with the H, joining with the H from the alcohol. When that happens, water will be eliminated. So this is what we'll actually have. And we're just keeping the color consistent so we can see where everything is coming from. So this is still H2O, we're just writing in a different way. So we can see that part of the H, one of the H's, the H actually came from the methanol and the OH came from the acid. So what would happen now? The water would be eliminated as that small molecule, and then let us look at where the joining will occur. So this part here is going to be joined to this part here. So let us just reproduce that. So we'll have an arrow to say what we get. So this would be, let's start from the left, would have CH3, CH2, then we'd have C double bond O, and then we're at the part that we just took off the OH. So we'd have a bond right there, and then we'd have the alcohol part now. O, then CH3. And let us just highlight the bond, the ester bond that was formed. So this is the ester bond that we just formed right here. And the ester bond was formed here. It's formed right here. So this is the part that we join in yellow. Let's make it a little more conspicuous. So let's use green then. So that's the ester bond that was formed. So to actually get the products that are, to actually get the compounds that would have given this compound, the formula of the compounds that would have given this ester, we would actually go in and we look in the ester bond, and we always cut. We would cut right here, right after the C double bond. Oh, let me draw a squiggly, a black line to represent that. So we cut the bond right there. When we cut the bond, we're going to have, we can now take the water molecule, split the water molecule, split it back into OH and H. And we're pretty much putting on back the OH where it came from the acid. And we're putting on back the H from the alcohol. So what would really end up with is CH3, CH2, CO, that's C double bond O, then OH. That's the acid, and would also have CH3, OH. So that's the fully displayed structural formulae of the two molecules that are produced when C is hydrolyzed. Part B. Ethanol is widely used as a solvent for making cosmetics and perfumes. State the name of compound D and identify the reagents and conditions necessary for ethanol to be converted into compound D. So this is ethanol. Well, it's labeled ethanol is here, and on the right-hand side, we have compound D, which is ethanoic acid. Ethanoic acid. So the name of compound D, ethanoic acid, and we get a mark for that. And they want us to identify the reagents and conditions necessary for ethanol to be converted into compound D. So we would need acidified, we'll need a very powerful oxidizing agent. So we need acidified potassium manganate 7 or acidified potassium dichromate 6. So we could write out the words or we could write the formula. Acidified potassium manganate 7, in bracket we could put H plus slash KMNO4, or acidified potassium dichromate 6 outer space here. So this would be H plus slash K2Cr2O7. All right, and 3 more marks on our tally. Explain how ethanol can be made from the fermentation of sugar. Include the chemical equation for the overall fermentation process. All right, so very important. We'll start out by just stating the sugar or sugar solution in aqueous medium is reacted with yeast, which contains the enzyme zymase. The conditions for the reaction, 37 degrees Celsius is the optimum temperature. It shouldn't be brought above that. And we need the correct pH. We don't have to state the pH. So the glucose would pretty much be converted into ethanol and carbon dioxide. At 12%, the yeast will be killed, and so the reaction would stop. And so then we would have to distill the mixture by a fractional distillation in order to get a higher concentration of ethanol. So that is pretty much it in a nutshell. So we're just going to write that down. All right, so the other thing that must be noted, like we need to state the correct pH because the enzyme zymase, they are pH sensitive. So if the pH is too low, it can render the enzyme inactive. And also we must state that the optimum temperature, the temperature used is 37 degrees Celsius. I hope this is clear. So let's just fix that. All right, and they said in part 3 now, for the last mark to give us the full marks, to give us the full 15, state one other use of ethanol. So we cannot state any of the uses that were already given. So they stated that it's used as solvents in the manufacturing of perfumes. So we'd have to use another use. We'd have to give another use. So another use we could give is that ethanol is used as fuel. We know about E10. So ethanol is added to gasoline. And I mean, ethanol by itself, it is used in spirit lamps. It burns with a clean blue flame. And just like that, we would have gotten 15 marks. This question speaks directly to chemistry and environment. This should be one of the more applicable ones. This is something we see in our everyday life. Part A, many metals undergo corrosion when exposed to certain conditions. Figure 2 shows an experiment where iron nails are exposed to different conditions. In test tube A, we have a nail in water, and it's also exposed to air. In test tube B, there's boiled water. The nail is in boiled water, and there's oil on top. There's a layer of oil on top of the water layer. And test tube C, this nail is exposed to dry air. State the 2 conditions necessary for the corrosion of a metal. So in order for a metal to corrode, these 2 conditions must be present: moisture and air. Moisture denotes the presence of water. So moisture and the air must be present. And this should give us an idea why folks are get very worked up when there's a scratch on the car. It's not that it's much ado about nothing, but when nothing is wrong with a scratch, but when it goes beyond the painting, beyond the layers of painting, and it has reached the metal. It's like getting a cut that has gone to the bone because we have a problem there. That metal is now going to be exposed to the elements, moisture, air, and that's a chain reaction. All right? Part 2. State whether corrosion will occur for each of the test tubes shown in figure 2. Give one reason to support your answer in each case. So test tube A, that has water and air. Yes, corrosion will occur. So this one has water and air, the two conditions necessary for corrosion. Test tube B, so corrosion, will corrosion occur? No corrosion. And the reason here, the layer of oil is blocking out air. Very reactive metals like sodium and potassium, they're stored under oil to ensure that they're protected from air. So oil is sealing off the air. And the fact that the water is boiled means that any oxygen that would have been present, would have been dissolved in the water, would have been driven out. So the oil now is forming a protective layer. So only water is present there. And in test tube C, we would expect no corrosion. And the reason, no moisture is present. And I think we've probably answered this in a sense. Suggest the reason why the boiled water was covered with oil in test tube B. And this was to prevent air from entering, more specifically oxygen, since oxygen is slightly soluble in water. Well, that's how the fish get it. So it's more than slightly soluble. Part B, aluminum has been used in the manufacture of various alloys because of its corrosion resistant properties. State one alloy of aluminum and its use. All right, the good thing is we're writing because I'm not sure how we pronounce it. I'm not 100% on the pronunciation here. So it's duralumin. And it's used to make bodies for aircrafts and cars. There's another one, magnesium, but they answer one, so we'll just let's stay at one. Part 2, explain why the corrosion of aluminum is beneficial. Can you believe it? Can something be corroding and it's beneficial? All right, so this is it. When aluminum reacts with oxygen, aluminum oxide is formed. Now this oxide, this layer of oxide actually adheres to this layer of oxide adheres to the metal, and it pretty much protects it protects the metal that is beneath the surface. So it's acting like a scab. It's similar to what happens when we get a cut and we have a scab being formed. The scab protects the rest of the tissue beneath it. So the layer of aluminum oxide that is formed adheres to the metal. It does not flake off, and it therefore protects the layer of metal that is beneath it from further corrosion. Let's get that down. Part 3, write a balanced equation to show the product formed when aluminum is left exposed to air. So aluminum is a solid plus air, oxygen, which is a gas, O2, and we'll get Al2O3, which is a solid. So In order to balance, let's start with 2 aluminum on the left, um, 2 aluminum on the left, 2 on the right. So we have 3 oxygen on the left, 2 on the right. LCM of 2, 3, 6. So we'll need 3 right there, and we need 2 right there. But when we do that, we'll have to turn this aluminum over here into 4. Oops. So this will now be 4Al solid plus 3O2 to give 2Al2O3. And just like that, you would have gotten 15 more marks. Please check out the links below this video for other videos like this one. Like, share, and subscribe.